This section will detail Boolean algebra and the various reduction techniques for Boolean algebra. We'll start off by defining what combinational logic really is. Combinational logic uses two or more logic gates to form a more useful complex function. An example of this is a combination of logic functions with our example. We have b equals kd plus hd. We can reduce that to b equals d times k plus h. The Boolean laws are cumulative law, associative law, distributive law, and we'll show you some equivalent circuits. But first, the cumulative law of addition, a plus b equals b plus a. Associative law of addition, a plus parentheses b plus c, close parentheses, equals a plus b plus c. Distributive law says that a times b plus c is equal to a times b plus a times c. These are some equivalent circuits for those laws. We have our x equals a plus b equals this equivalent x equals b plus a. And our x equals a times b times c equals x equals b times c times a. And we have this equation, x equals parentheses a plus b, close parentheses, plus c equals the equivalent of a plus parentheses b plus c. And we have this equivalent form using a times b times c in parentheses is equivalent to a times b times c in parentheses. And we have the third form, a times b plus c in parentheses equals a times b plus a times c. And a more complex version is a plus b in parentheses times c plus d in parentheses equals a times c plus a times d plus b times c plus b times d. It's a lot longer, but it's also the exact same equation. We also have the gate form shown here and up top as well, and the previous ones. The rules for Boolean algebra are as follows. Rule 1. Anything ended with a 0 is equal to 0. Rule 2. Anything ended with a 1 is equal to itself. Rule 3. Anything ORed with a 0 is equal to itself. And Rule 4. Anything ORed with a 1 is equal to 1. There are 10 rules. These are the first 4. So in Rule 2, we have x equals a times 1 equals a. So x equals a. And shown by the truth table form. For this is an AND gate. This is an OR gate. We have x equals a plus 0 equals a. And the same follows, x equals a. For the the fourth rule, we have a plus 1 equals 1. So x equals 1. Rule 5. Anything ANDed with itself is equal to itself. Rule 6. Anything ORed with itself is equal to itself as well. Rule 7. Anything ANDed with its own complement equals 1. And anything ORed with its own complement equals 1 for Rule 8. And these are the equivalent circuits as well as the examples with our truth tables as follows. Rule 9. Anything complemented twice will return to its original logic level. And Rule 10. We will show through the table exactly how these two equations are manifested. This is Rule 9. We have our A going through the inverter, so it switches sign once, and then going through another inverter, switch sign again. So x equals the double negative A equals A, as shown in the truth table. And this is our two equations. We have our inputs A and B, the simple 4 possible combinations, and our formulas judging by those combinations. And the second equation is exactly the same, except for the equation part, obviously. This is a summary of the laws and rules of Boolean algebra using combination logic circuits for reduction techniques. You'll see these, but you'll also see simpler forms of reduction later. Simplified combinational logic circuits using Boolean algebra. We use equivalent circuits that can be formed with fewer gates. This is also cost is reduced and reliability is also improved. First form of reduction is the DeMorgan's theorem. This is used to simplify circuits containing NAND and NOR gates, more than one negative sign in the equation, as shown by these two examples below. The DeMorgan's theorem states you break the bar over the variables and change the sign between them. Inversion bubbles are used to show inversion rather than inverters. Use parentheses to maintain proper groupings. End up with sum of products SOP form. Bubble pushing. This is shown in figure 560. It's a shortcut method of performing equivalent gates. This is an example of bubble pushing. You have your regular AND gate here, and you put 3 bubbles and change the gate type to an OR gate. And as follows, with the following 4 examples, you take the original gate, put bubbles on it, and switch the gate to its opposite from OR, AND. Universal capability of NAND and NOR gates. NANDs can be combined to form all of the gates, as well as the NORs. We'll see this by these diagrams right here. With our first one, we have x equals negative a times a equals a. It simplifies it down to 1, because you can have one input and change it following this form here. And the same with the others. It takes one gate off and converts it, as shown here as well. You have one input, same input for both, and it inverts to just one. And or invert gates for implementing sum of products expressions. There's 2 types of expressions here, the POS and the SOP form. The SOP can easily be implemented by using an AND or invert gate. Karnaugh mapping will be the simplest way to understand how to reduce Boolean algebra. This is the most important way and useful way for students to understand how to convert their long Boolean equations into short, simple equations that can easily be created into gate form. This reduces circuit costs as well, reduces physical size, and gate failures. It's a form of graphically showing the output level for all possible input combinations, and you move from one cell to an adjacent cell. Only one variable changes at a time. And you can encircle adjacent cells in groups of 2, 4, and 8, and you gotta watch out for wraparound technique. This is because some equations have wraparound that you can simplify more than you probably think you can. And the summary of this segment is several logic gates can be connected together to form combinational logic. There are several Boolean laws and rules that provide the means to form equivalent circuits. Boolean algebra is used to reduce logic circuits to simpler equivalent circuits that function identically to the original circuit. The DeMorgan's theorem is required in reduction process whenever inversion bars cover more than one variable in the original Boolean equation. NAND and NOR gates are sometimes referred to as universal gates because they can be used to form any of the other gates. The AND or invert gates are often used to implement sum of products equations. And Karnaugh mapping usually provides a systematic method of reducing logic circuits. This is the one I would suggest to use because it is more of a graphical representation rather than staring at numbers and letters